These neurons and their electrical activity and chemical exchanges at synapses allow for central nervous systems to interpret sensory information, plan motor actions, process information, plan for the future, hold memories. They allow great complexity in processing. At some point, the more of these neurons that a brain could fit, the greater the complexity of processing which would be allowed. And so the question arises, how could brains pack greater volumes of neurons in a small space? One way is to increase the surface area of a structure. And as one can see here in these images of the cerebellum, not only is the outside cerebellar cortex highly folded, but also there is a folding of the deep cerebellar nuclei, which increase the surface area and the number of soma which can be held. As you look at these shark brains, some of them have very large cerebellums, which are highly folded, once again to increase surface area. While there are soma deep within the cerebrum, in deep cerebral nuclei or basal nuclei, the vast majority of soma are in the outer several millimeters of the cerebral cortex. And so the cerebrum can increase the number of soma and the complexity of its processing by increasing the amount of the surface area, given that the surface area is where these soma are, in the first couple millimeters of the cerebral cortex. And so when one looks at the cerebrum, whether it be here in the human or in a pig, one observes a highly folded cortex with both sulci, these are grooves, the singular is sulcus, which then create folds known as gyri, the singular being gyrus. The cerebrum did not begin its development with gyri and sulci, as you can observe in the cerebrums of the shark, the perch, and the frog depicted here. When mammals evolved, the cerebrum did not have a complex set of gyri and sulci, as you can observe in the mouse, in the insectivore, in the shrew, and in the opossum brains given here. Then, if you were to look at the brains of, say, lemurs or primitive monkeys, you could see that some have a smooth cerebrum, some have a folded cerebrum. Thus, the majority of the gyri and sulci which one observes in the human brain would not have direct homologs in the brains of the majority of mammals. Even if other groups of mammals did develop these folds, they might have developed a different set of folds. Some of the folds which we observe in humans evolved in early primates, so primates share some folds that non-primates lack. Anthropoid primates, which would include the monkeys and apes, would share some folds and grooves that lemurs lack, and so forth, as one proceeds through the catarrhine primates, through the apes, through the hominid apes, etc. One observes that the folding pattern of the cerebrum becomes closer and closer to the pattern which one observes in humans.